team, welcome to my first class on direct current circuits, Physics 206. I wanted to talk to you a little bit about it. I understand that a lot of people were confused. I'll be honest, like this topic was a little bit confusing for me as well, and I wanted to clarify some things. So even though it was a 60 or 70-minute class for the last one, I will try to make it at most a 20-minute class to talk about little subjects that were pertinent for the lesson, and as well do some exercises that will help you understand Kirchhoff's rules. So I have Kirchhoff's rules displayed here because they're extremely important in order to do our loops around the circuit. So the first thing that we identify in Kirchhoff's first rule is that the sum of all currents entering a junction must equal the sum of all currents leaving that junction. So what it means by that, and I wanted to clarify this because this is one thing that was I was confusing G1 hour, and I apologize for that, is that whenever there is a junction point, and let's say that this is right here, this is a junction point, and this is another junction point. And the reason why they're junction points is because different currents are passing through this junction point. So let's say this is current I1, and let's say that this is current I2, and right here is current I3. Identifying these currents and their direction, we can identify that the currents going into the current, which is in, are identified as I1 plus I2 because they're going into that junction. But what's coming out is I3. Thus, everything that comes in, the sum of everything that comes in, is equal to the sum that everything that comes out. The same can be said for this one right here, this junction right here. So we're still in I3 here, I3, but now it hits another junction. We know that here in this section is I1. So coming out from here is I1 as well, current 1 as well. And coming out from here is current 2. So identifying as I1 plus I2 is equal to I3. In this situation, I3 is the thing that's going into the junction. Okay, in. And these two are the currents going out of the junction. Thus Kirchhoff's rule. So we were having issues, and that was something that I take full responsibility for. We were having issues with identifying, like, where is the current. If this is current I1 and this is current I3, what's the current here in this spot? It would still be I1 because it hit that junction right here, and it's back to the current split, I1 and I2. So in any junction, these two junctions have to equal each other in one way or another. The currents have to meet again. Right here. Okay? All right, so that is rule number 1. And that will help us with the actual understanding of Kirchhoff's loops as well. Okay, now rule number 2. It says the algebraic sum of changes in potential around any closed circuit path must be 0. a closed circuit path must be 0. So basically, if I do my loop around this circuit, it means that after I do my loop, the sum of all the voltage or the changes in electric potential around that loop would equal to 0. One thing I want to clarify about voltage in general. So voltage is in reference to something that you pick. It's very much like potential energy. So let's say that this is a mountain, right? And I say that this mountain right here is 12,000 feet. How do I know it's 12,000 feet? It has to be in reference of something. So if I pick 12,000 feet, and this is water right here. Let's say that this is C. From here, and let's say this is 0 feet, right? Let's just say, like, identify that. Then yes, this would actually be 12,000 feet. Because now I am taking the difference from my final position to my initial position to get the measurement that it is actually 12,000 feet. But if I pick my reference point to be from the sea level, and my sea level is, let's say, 500 feet below sea level, then my reference, my height won't actually be 12,000 feet. My change would be 12,500 feet. So it is very much like the same way for electric potential, where I have to measure, or not voltage, I'm sorry, in terms of voltage, where I have to measure in terms of a reference point that I choose. Okay, so I wanted to clear that out. So whenever I say, okay, let's measure the voltage, and I say, like, okay, so from here to here, I want to know the voltage. So because I am picking these two reference points to measure their voltage. Okay? All right. Now let's talk about why is it 0. So we are here. This is a good example. This is the battery right here. And the battery gives out 12 volts. So from 0 all the way out to 12 volts, it increases. So now the circuit itself has 12 volts. Okay? A voltage graph as we travel around the surface. The voltage increases as we cross the battery. We're crossing the battery, boom. But then it decreases once we hit a resistor. Okay? And that voltage across the resistor, when we decide, okay, this is our resistor. Actually, I already have it here. From here to here, and we measure the voltage across the resistor, it would give me IR1, right? This part right here. This little piece right here is the value of the voltage across the resistor. That same voltage is the thing that decreases the overall voltage around the circuit. So it decreases that amount through the resistor. And then it decreases again when it passes another resistor, all the way down to when it finally gets back to the battery at negative, where it's 0. Okay? I wanted to clarify that, and that is Kirchhoff's second rule. Now, let's talk about the circuits, the loops in general. we usually let you know that it's important to identify like, hey, write down from here to here, because you're measuring the voltage, right? And voltage is in reference to 2 points. So when we're saying reference to 2 points, I'm going to continue doing the dots. Actually, let me erase this right here. Okay, so this is the junction points. Right here's another one. Then here is another one. It's not a junction point. It's just points that I'm putting on into the graph. Okay. Then here, and here. And the reason why I put these dots in is that if I take my voltage meter, right? If I take my voltage meter and I put in, hey, I want to measure the voltage from this reference point, and let's say that this is A and this is B right here, I can measure the voltage between these two. If I put my voltage meter in here, I can say, okay, from VB minus VA, because it is the change in electric potential, then I know the voltage of that battery. And we've seen that through our tests that we've done online with Phys Ed. Okay? But I don't want to confuse you too much with the dots. I'm just going to let you know, like, hey, let's use these in this because these are the junction points to identify the current. And this is just all, it's just me picking the current itself, like just like saying a normal direction. So then I decide my loops. I can decide to start from the battery, around, and end up back up. I understand that going through the loop rule, after I go through the loop, all these, the sum of the change in electric potential should be 0. The same goes to the second loop because, well, remind you, this is loop 1 is a closed loop. And then if I decide to do a second loop here, and I follow the current, then that second loop, after I get back to the battery, it should also equal 0. Okay? But it doesn't have to be just those 2 loops like I did it in class. I could actually say, okay, I want this loop just as long as I don't repeat the pattern. And I can say, okay, I want to take outside this, I want to take this loop as well. And you can see that in the book as well, where we have loops, different loops that we try out, and I have it right here. You see this one right here. This is a perfect example where it's doing a loop here and C, D, E, F, C, and then it decides to do another loop outside and does a loop all around the circuit, the humongous circuit as well, A, B, C, D, E, F, A. Okay? All right. So now that I talked to you a little bit about that, let's talk about this matter. So the direction of travel is with the direction of the loop, right? And following the current as well, we identify that if I'm following the current and I'm also following like in the direction of the loop, going from A to B of the resistor, then the voltage across the resistor picking my voltage meter and picking A and B, the voltage across the resistor will be negative because I am choosing from low, or from the end, because this is the end, to the beginning. Subtracting that. That's how you usually do a change in electric potential. You do the end first minus the beginning to get that change. It is the same thing going on here. If we would decide to do it the other way around, where we're going against the current and we're doing the loop around in another direction, then the way that we would start is, again, since we're going in this direction, right? This is the end, and this is the beginning. And we would subtract the end minus the beginning. And this time it would be positive. Now, the reason why one is positive, this one is positive, and this one is negative, is that you have to remember when we're going through a current goes from high to low. And voltage here is decreasing, like the voltage here decreases, not decreases, the voltage across it let me just paraphrase it. So instead of saying that the current slows down due to the resistor, right? So that means that across the voltage, it will go from a high electric potential, a high voltage, to a low electric potential. So high, low. The same deal happens here, where this is high electric potential, low electric potential. The change in these two, following the order that I told you, end and beginning, in this situation will give me a positive value. In here, for the batteries themselves, remember, batteries start from, at this point, the battery is low, like we shown in the graph, right? The show, it starts from low, and it ends up high. Okay? Then, because we're going in a direction of travel, so high minus low will give me a positive voltage. In opposite of, like going in the opposite direction, this time around, it still applies low, high, but because it is a change and we always start here at the end, this is VA minus VB, where we initially start, the beginning. Okay? And that subtraction, that change, will give me a negative number. Okay? Okay. Good stuff. Now let's do our famous problem one more time. Problem number 2, expert TA. And we explained this in class, and I would like to discuss it one more time just to make sure that we reemphasize. If you already know how to do it, no matter, skip to this next problem that I'm going to be doing as well. And this one has a parallel circuit. Okay. So the first thing is we look at the diagram and we identify that there's current going here, current 1, going into this junction A, and it's splitting into current 2 and current 3. That's the first step. So following Kirchhoff's rules, I will decide that instead of, I'm going to pick 2 loops. I'm going to say this loop right here around. And then I am also going to pick this loop. Let me pick this one around as well. This one, loop 1, is going to be clockwise. Loop 2 is going to be counterclockwise. It does not matter which side you choose as long as you are consistent with these rules right here. Okay? All right. So let's start off with identifying our junction rule. So we said I1 is equal to I2 plus I3 because I1 is going in and I2 and 3 are coming out. And this is for junction A. To clarify, for my G1 students, junction E is the same but inverse. So current 2, it continues going from A, B, C, D, all the way back to E. So current 2 is here as well. And here. Okay? And current 3 following it all the way around the circuit, current 3 is right here. Okay? That means that following the junction rule, I can say I2 plus I3 equals I1. But we use I2 for the remainder of this loop around here. And it switches back once we get to this point. It switches back to I1 because I1 at this is the junction at I1 for I1. Okay? So we only need one equation for the current. And I'm going to use this path right here so I can start writing EMF for the battery, electromotive force. And that's a positive because it's going from low to high, and we go from, okay, so the electric potential at C minus the electric potential at B, and here is 0, and here is 10.5, thus it would be 10.5. Okay, so that's the first one. Then the resistor, remember what I said, resistors decrease the voltage, and we have current 2, R1, because current 2 is in this side of the circuit, minus I2, no, I'm sorry, not I2, I1, R1, we're here now, and then minus I2, R2 equals 0. So that is our second equation. This is our first. Okay, notice my negative numbers, my negative resistors, and it's following the direction of travel, right? Because I'm following the current, and the current is telling me if I'm following the current in the direction of travel, that means that it's a negative value. Okay? And understanding that every time that I pass a resistor, what I'm analyzing is the change in in voltage crossing the resistor. Okay? So going back here, then finally equation 3. Write this down. Equation 3 would be, let's start with counterclockwise. and following the current as well. And, rule of thumb, maybe follow the current. I think that would be easier. Just follow your, like, a good guideline for it. E2, starting with the battery, minus I3, current 3, times resistor, little resistor 2, minus I3, big resistor 3, minus I1, because now we're here, I1, resistor 1 equals 0. So now the question asks you to find current 1, 2, and 3. So this is perfect because you have 3 equations, 3 unknowns. Now you can solve for the actual problem. And I saw some of you that were saying that, hey, I2 is actually a negative value. So if you get a negative value, it does not mean that you are incorrect. It means that despite the direction that it's telling you here, in this current, despite that direction, in actuality, the current in I2 is inverse. It's going downwards. Okay, that is what it means because you got that value. It does not mean that you're wrong. But we do use these directions to eventually let us know the actual direction of the current. Okay? And you are able to solve for current 1, 2, and 3 with these 3 equations. Now let's go into this one right here. This is problem 43 from chapter 10. So this is another good problem. And it's fairly easy in the sense that it's not requiring you to, it's not really saying, okay, this is a different resistor, this is another different resistor. All of them are actually saying, okay, so let's just treat this as this is the same resistor as this resistor in terms of value, and R is the same resistor but multiplied by 2. The same with the voltage. Voltage here is the same value as the voltage here. Okay? So it's asking us to do 3 equations that are 3 currents in terms of R and V. So let's start off with identifying the junctions. The junctions, because this is where the currents meet, the junctions are where the currents meet, is here, junction A, and junction B. Okay? So this part right here is telling me that in junction A, the current is equal to I2 plus I3 is equal to I1. This is junction A. The same can be said for junction B. This time around, following my current I1, I realize that they split up at I1, right? Because I'm following the direction of I3. So if I follow the direction of I3, following all around, it goes back in to junction A, in case you had any questions on that. And then I2 goes in this direction, again following the same procedure that I had for I3. I just follow it around, and I know the direction of I2. So it would be the same, but now everything going in, which is I1, will equal everything going out, which is I2 plus I3. We only need 1, so I'm going to erase 1. But I wanted you to see that because again, it's re-emphasizing one of the errors that I made at the beginning that I want you to make sure that you understand. Okay, so I can do this as well in many ways, but I'm gonna decide to do a loop. Every closed circuit, I'm gonna do a loop. Okay, so this right here is a closed circuit, and I'm gonna go following the current. Okay, just to be consistent. So I'm following the current. This is loop 1. And this right here, this other part right here, loop 2, will go around. And I'm following the current as well. So I'm going to go around here, back around, boom. Okay, so that would be loop 2. Loop 1 is fairly easy. Loop 2 is a little bit more challenging just because there's a parallel circuit, and I'll touch on that now. Let me hit back. Ooh, kind of messy. What happened here? There we go. Back to normal, or sort of. Let me rewrite it. Loop 2. Surrounded. Okay, so let's do loop 1. So we already have equation 1. Now let's do equation 2, which is loop 1. And loop 1, if I follow the pattern, I start from V, the battery. It is positive, remember. Low to high for batteries. Then high to lows for resistors. So current 2 times R, okay, it's just R, minus current 1 times R, because now I'm here, right? And that will all equal to 0 because there's nothing else. There's nothing else in that loop. Done for this one, for loop 1. If I decide to go for loop 2, well, now I'm going to loop 2. I have to do loop 2, which is equation 3. I'm going to start off with the battery. And I start with V. But then I hit this parallel circuit. So remember what I said about parallel circuits? So parallel circuits, they have the same voltage when measured here to here, here to here. They have the same voltage all around. Okay? But the current changes because just like the junctions, in here, I3 is split into 2 different currents. And I'm going to call this IA and IB. All the way up to when they meet here, where they form again as I3. And if you have any doubts with this, just remember the junction rule. I3 equals IA plus IB. Here, at this junction, it's IA plus IB equals I3. Okay? So just so you know that the current changes when it's going through a parallel, but once it hits that junction, again, they add up and become I3 again. Okay? So in a junction, in this junction, understanding that voltage stays constant, but the current changes, I can go something to the effect. Okay, so I, and I'm going to write AA and IB. IA is equal to the voltage that already has here, right here, the battery, over the resistance to R. Okay? Over the resistance to R. That will give me the current because I'm following Ohm's law as well. Comma. Now IB is the voltage stays constant, to R. The same deal. Now, if I were to do Kirchhoff's law, where I have I3 equals IA plus IB, then I would come out with switching out I3 equals V over R2 plus V over R2 or 2R. I can switch I3 now too, because since voltage is still the same in a parallel circuit, then I3 voltage, which is constant, and the overall resistance at the parallel. Okay? So this is basically letting me know the overall resistance that comes out from this circuit that we have here. So this is the circuit that I redrew. These are the two resistance, 2R and 2R. And what I want to do is just create one, saying, okay, so this is the equivalent of this, or parallel. Okay? Erasing this. This will equal to V2R, V over 2R, plus V over 2R. And this will scratch out, because since these two, all these are constant, I can cancel these out. And I am left with R parallel equals 2 over 2R, because now I am summing these two together. And I have 1 over R. To get R parallel, I just have to flip them, and I get R as being the value, the total resistance accounted for in the system. And now you can treat it normally like these other resistors. Okay? There's an equation for this, and it's found in your book. It's the same concept. I go the long way so you can see where the equation comes from. But it's basically saying, like, hey, in order to get the resistance over parallel, it's just summing up, or the resistance over parallel, it's just summing up all the different resistance, and that would equal the resistance in a parallel. Okay? But I like to go in this direction so I can teach you. All right, so now that I have this, and all this is accounted for as just R, then I go, okay, minus I3 R, okay? Then going back to V parallel, V of R parallel, just so you know where it comes from. And this is I3. I just bring the R parallel to the other side, which is R. And that's how I got the value. So I3 times R minus I1 times R. And that all equals to 0. So now, all you have to do is solve for the current, and you should be able to find it. You should be able to find I1, I2, and I3. Let me give you the answers for that so you can try it out yourself. I'm going to put it right here like this and see if you get the same answers. Okay? So for I3, it's V over 3R. For I2, it's V over 3R2. And for I1, it is equal to 2V over 3R. Try it out. Let me know what you think. So yeah, maybe this class took a little bit longer than I thought, and I'm pretty sure a lot of you are going to put me on speed dial or like that thing that you do where you increase the velocity of the video, but that's okay. Anyway, I hope this video was helpful and it clears some stuff. As always, I will continue doing more videos to help you out for this, and hopefully I can get some feedback out of it. Anyway, I appreciate it. Thank you so much for seeing the video, and I'll see you next time. Bye.